All right, Michael, we are live. We are streaming whenever you're ready.
All right. Welcome back, everybody. Took a break. So we'll be continuing the wood and materials list discussion. This one's going to be very specific to single phase cooling. And this is actually a list that a team that I'm working on at Intel put together. So it's going to be a very specific wood and material list, not encompassing, of all single phase lists, but we're going to go into a little bit more detail as far as which fluids we've looked at and we've tested and compatibilities that we found that work well together. So I'm going to give a quick introduction, show some slides on the fluids, go into the specific suppliers that we've worked with, and then going into the actual wood materials list themselves. All right, so obviously liquid cooling is important for cooling highest power components, cooling efficiency, and even higher compute density. This specific wood materials list, it really does go hand in hand with the fluids we discussed. So it really is important that these are the lists that go with the two suppliers that I show, and these are the ones that we really went and did testing. Compatibility really is important for two major reasons, and that is for corrosion and avoiding biogrowth. Okay. All right, so here's the specific fluids that we were looking for. So when we started our effort, we were looking for some polypropylene glycol. And we looked at both 55 and 25% glycol. And the reason why we really looked at 55% was for shipping, for that shipping temperature of minus 40 degrees C. To survive shipping in an airplane is the only reason why we looked that low. In general, we strongly prefer a lower percentage, like 25% glycol, because that's really the amount you need for good biogrowth control. And then with 25%, you've also got more water, so thermally it's a better material to use. But again, to encompass shipping constraints, so if it's going to be air shipped, if we ship a primed piece of equipment, we would need to support 55% glycol. Now, as far as 55 and 25%, those two materials, if they're from the same vendor, and it's just a percentage that can be mixed after the fact, like you'd ship a small primed component and include it into a big system with 25% glycol, that would be fine as well. Or you can ship components dry and prime them on site. Okay. A couple other comments about the fluids. So this is obviously wood materials, very important compatibility. Quality requirements of fluids needs to be determined by the user. So for your particular case, what qualities do you need? And maintenance of fluids, so filtering, etc., are all things that need to be considered, in addition to the operating range of temperatures. All right, so specifically, these are the two suppliers that we ended up working with. We had a Dow with the Dow Frost material, again, both the 25 and 55% concentration, as well as a Huntsman chemical, a Jeff Cool from Huntsman. Both are offered in 25 and 55% polypropylene glycol mixes, and are available in 47 countries globally. These fluids are not interchangeable, so even though we looked at both of them, we looked at them independently. So either one or the other would work. There is a slight difference between the two chemicals. In addition to the polypropylene, they both add a little bit of their secret sauce, as it were. But these are definitely the two that we've done the most testing on in-house. Okay, so from our testing, what materials have we found work best? And again, this is the materials that we've tested extensively. There might be other materials that still work with these fluids, but these are the ones that we've seen the best results with. Best results as in, least reactions. So as far as elastomers, we recommend EPDM, Viton, GF, and ETB. So these are the ones that were the most stable when we were testing. Tubing in general, we looked at a lot of different types of material for tubing. And either the elastomer, the EPDM, or in the next section, the plastics, something like FVP, are two materials that are good for tubing. And again, these are materials could be used in any use case. So it could be tubing, could be plastic fitting, etc. So leading into the plastics then, so the plastics that we looked at were FEP, so fluorinated ethylene polypropylene, the PTFE, polytetrafluoroethylene, PP, polypropylene, PEEK, polyethyl ketone, and HDPE, high density polyethylene. We had also looked at a few materials, so polysulfone and polyphenylene sulfide, and both of these we've moved away from. Main concern was with the sulfur content of those materials. We just moved away from them, so kind of reducing our risk. All right. So next list is our metals. So these are metals that we found were compatible. We try to stick primarily with copper. So a couple of different alloys of copper were used, and they're listed here. We also use stainless. Stainless is pretty frequently used in liquid cooling, but no other major metals used. We did look at titanium for a few small minor components to some extent, so that was also in there. And as far as brazing filters, the brazing material that we looked at was a B cup 5, which is copper, a little bit of silver, and a little bit of P is phosphorus, I want to say. The silver, we're trying to avoid large amounts of silver, so we're actually looking at other brazing materials as well. But this one we've tested, and in our test setup, we saw little to no reaction. So, and the brazing material and the titanium were recent lists. So we've shared this material before. It's not in a full white paper yet, but we have shared these material lists in a few different OCP presentations. All right, so test methodology. So this is the test setup that Intel has used to look at the fluids. This is our fluid loop. Now we ran our test for a full 180 days, but with some of the materials that we looked at, we would see reactions in tens of hours. So to fully validate for the system, we were targeting 180 days. That was our target number, and it's a factor of many things. So the temperature that we're running the setup at, how many cold plates we had in our setup. You can see from the illustration on the right that we had cold plates in parallel and in series. So basically, the more cold plates you add to your system, the less time you have to run your overall test, because it increases the odds of a failure. And if you have no failure, that proves that your compatibility is good in even shorter amount of time. Again, the materials that we looked at were the ones listed above: the stainless steel, copper, vitron, etc. And our parameters here that we looked at were pressure, fluid, case temperature, flow rate through the various channels. Testing that we did after the fact was characterizing the fluid's pH, conductivity, concentrations from corrosion inhibitors, particulates, etc. So these are the tests that we ran after to make sure that the fluid is as close to its starting conditions as it was at the end of the 180-day testing. Okay. So that's really the quick description of what we've done with our testing. So with that, I'm going to flash up quick the OCP cold plate wiki and project channel. So I'm running the cold plate sub project. We meet every second Wednesday of the month. So if you're interested in this topic and others, please contact me. With that too, I can open up for the next few minutes. Looks like I say about 5 or 6 minutes for Q&A. Also, quick shout out to Sean Silvapalan. He is a PhD in material science for Intel. He's really the material science expert on this project. All right, so go ahead and type in questions or join the Zoom audio if you have anything for me.
Hey, Michael, looks like you do have a question from Dale Sartor.
Okay.
in the FM virtual chat. He's asking how will the latest wedded material list be spread out to the industry? How will that be distributed?
Good question. So far, at least, what we've been doing is things like this forum. So we shared a list like this both in the open conference earlier this year, and I believe we shared it last year. Um, Going forward, we might do a white paper. I'm not sure. But yeah, we're still looking at how we want to communicate it. Intel itself has some documentation, basically liquid cooling design guide that we share with some of our customers. Yeah, but most likely we would like to do a white paper in the future. All right, any other questions? In the chat or otherwise?
Nothing else that I see. We do have significant number of folks watching this presentation. I think we've got around 50 folks still on watching. So
Okay.
if anyone has a question, oh, here we go. From Ian Scott, what field life do you expect the 180 days test to correspond with?
That's a good question. I'm trying to remember. Typically, we're looking at about a 7-year life of our products. So I believe that was the lifespan we were trying to investigate. I would need to double check it. There's a slight possibility that it was more like 5 years, but typically 7 years is what we're targeting. Yeah.
Got another question that came in. Could you explain more about why PPS was removed?
Why PPS was removed? Again, the sulfur content was the main reason. Just concerns with reactions. Looking at my notes real quick, see if I had any elaboration on that. Unfortunately, the specific concerns with sulfur, I'd probably need to pick Sean Silvafon's brain on that one. But the sulfur was the main concern that we had, and the reactions in the different fluids. So. Sorry, I didn't have a better answer for that one. Any other questions I can try to answer? Sean,
All right. Looks like that's all the questions we've got. Thank you so much, Michael. Really appreciate both that presentation and all the work that you're doing in the cold plate group.
Yeah, thank you. And I will be presenting later on with some leak detection as well. So hope to see people later.
Great. All right. So with that, the next item on our agenda is Mr. Glenn Charest with an update on the ORV3